So, hello students, welcome to another class on vectors, and already we have discussed the type of vectors and how vectors are working in addition, subtraction and multiplication. We have also seen how the coordinate system will work when the rotational things are taken care of, like cylindrical coordinate system and spherical coordinate systems. And we have also seen the transformation of one, you can say, one point in coordinate system into another point in spherical or cylindrical coordinate system. A few examples already we have discussed. Today, the main topic will be the vector calculus. So you can say the gradient of a scalar, divergence of a vector, and we'll see the divergence theorem, Karl, Stokes theorem, and Laplacian of a scalar. So these were the top. These will be the topics today we will discuss in detail. Myself, Dr. Pradeep Sharma from University of Engineering and Management, and we are starting our lecture today from gradient of a scalar. I am just taking one example. Suppose you want to calculate the temperature at any point in the room, and the room you are describing in your visualization as a Cartesian coordinate system. So that point P is somewhere, and we are taking at suppose P1 x y z. So suppose T1 is the temperature over there. Okay, and T2 is another temperature at any other point P2, where x plus dx, y plus dy, and z plus dz are taken care of. Okay, so we can say that the differential distances dx, dy, and dz are the component of the differential distance vector dl. So this dl is dx ax, dy ay, and dz az, where the ax, ay, and az are the unit vectors in those directions. So we can say the differential calculus, the differential temperature will be dt, T2 minus T1. So delta T by del x dx, delta T by del y dy, and delta T by del z dz. So this can be the differential temperature. So we can find that dx is equal to dl dot ax. Already we know in from the unit vector definition, and we can write the equation like delta t by del x ax dot di, and in the same manner, so we can take this complete vector dl out, so that delta t by del x ax, delta t by del y ay, delta t by del z az, complete bracket dot dl. So easily we can find out that the length element whatsoever the length element vector we have taken out, and it's the dot product with the multiplication of this. So how we can say that vector inside the square bracket, it defines the change of temperature del dt corresponding to a vector change in position dl. So this vector is called gradient of scalar. So what is that bracket inside? So the value inside the bracket is, you can say, delta t by del x. So the change of temperature in x direction. So this is the unit vector delta t by del y. Again the change of temperature in y direction and the change of temperature in z direction. So what we are considering, basically we are considering the change of the scalar quantity with respect to the axis. So vector is called the gradient of scalar. Okay. For Cartesian coordinate system, we can have del v by del x ax, del v by del y ay, del v by del z az, right? And for circular cylindrical coordinates, if we find the value for the same, so del v by del rho a rho, 1 by rho, del v by del phi a phi, del v by del z az. Because in cylindrical coordinate system, we are considering that there are three coordinates, rho, phi, and z, right? So in a spherical coordinate system, we have r, theta, and phi as our three coordinates. So we can say in spherical coordinate, delta v by delta r, ar, 1 by r del v by del theta, a theta, plus 1 by r sine theta, del v by del phi, a phi. The derivation definitely we can discuss, but right now we are skipping it. We are just focusing on the, you can say, the final result. We will be using these equations wherever we require. Definitely, in most of the cases, the derivation for these equations are not required, and in most of the applications also in numericals directly you can put these values, and accordingly you can get the results, because it is just coming and going back, that it is basically the change. You can say gradient is the change of the value with respect to the position, with respect to the change of position. So if we go from one point to another, then what will be the value, what will be the change of that scalar value, scalar point function, when we are moving from one point to another, one position to another position. So it is basically the change of, you can say, the scalar value corresponding to a vector change in the position, right? So that we need to take into account. Few examples are that, like find gradient of these scalars. So scalars are e to the power minus z, sine 2x, cos hyperbolic, and y. So these are the values. So it is given. You can say in Cartesian, cylindrical, and spherical system. The three problems are there, and if you solve these problems like this, first one, Cartesian coordinates, delta v, you put the value for the gradient in Cartesian, you put the value for the function in everywhere. You have to find the del v by del x first, del v by del y, del v by del z, and the unit vectors ax, ay, az. So you can find that these are the values after the derivation with respect to x. This is the value after the derivation with respect to y, and this is with respect to z. Now the second one is a gradient for circular cylindrical coordinates. If you put the values and again you differentiate with respect to rho, phi, and z, you will get directly the result. And the same for spherical coordinates, right? So these are very simple to find, but you have to visualize the thing in cylindrical coordinate, or you can say in spherical coordinate system accordingly. Now we are moving to one important part. If we are considering that, okay, the vector is operated by a, you can say the vector is operated by a del operator. So then we are having some physical significance of that. So divergence is basically gives an idea about the field, that whether the vectors, or we can say the vector, the physical quantity, which is a vector physical quantity, is you can say coming out of that point or going into that point, right? So we can say that divergence refers to, you can say, okay, this is there. So the flux, you can understand that this value a dot ds integral over the whole closed surface, this value if you consider only, then this is the flux. Okay, so if the flux is outward, then the positive divergence. If it is you can say the net flux is into any point, then negative divergence. And if we say the flux coming total is equal to the flux going out, then it will be zero divergence, right? So divergence can be written as the outward flux per unit volume when the limit of that small volume tends to zero. So it's the limiting case of the elementary volume is tending to zero, and when the total flux to small elemental volume ratio is defined as divergence. So it is given by del dot A. So this A is the vector field, and then this del operator is again a vector field, but you can see the dot product. So divergence A will give you a scalar result, right? Will give you a scalar result. So divergence of a vector field, but we can say that what is A dot ds, already I have discussed that this A dot ds is the flux. For example, we are having one cube structure over there, one cuboid structure over there. So you can say that's a closed surface S, but there are 6 surfaces, right? top side, below, right side, and the left side, and you can say the front and the back side. So point P is somewhere. So when we are finding A dot ds, so all the integrals, the sixth surface integral, front, back, left, right, top, bottom, A dot ds, right? So V is the volume enclosed by these surfaces. So V is the volume inside that. So and for Cartesian coordinate, the divergence is given by del Ax by del x, del Ay by del y, and del Az by del z. And the circular cylindrical coordinates, easily we can find out the del dot A. Here you can understand that the del is the cylindrical value what we had in our gradient part, right? And this A is the vector represented in cylindrical coordinate system. That is why this A rho, A phi, and Az value will come. For spherical coordinate system, again this del will be in spherical coordinate system, and A is also in a spherical coordinate system, and then we find the dot product of those two. Then we will find that it is 1 by r square del by del r square ar, plus 1 by r sine theta del a theta sine theta by del theta, and plus 1 by r sine theta del a phi by del phi. So this way we can find these values. Again, the few examples are there that I find the divergence of the vector. So first vector is given in Cartesian, another is in cylindrical, and then the last one is in spherical. So if solution we can easily find del dot p. So we are putting del in the Cartesian value, and the p value again is given in that. So if we find this value, you see x square yz ax and xz az. So you can understand that over here the three parameters are there, so it can be differentiated with respect to x, but over here the y parameter is not there. So we can find this x square yz, its value is 0, and that can be differentiated with respect to z also. The value, the answer is 2xyz plus x. So this easily you can find out using the concept of dot product. Now divergence for circular cylindrical coordinate, we have to put the del operator in cylindrical, and then q is in cylindrical and differentiate with respect to rho, phi, and z. The resultant will be very simple to find. In spherical coordinate system also, the value of del is in spherical, w is also spherical. Take the dot product, and the easy solution to cos theta cos phi will be evident. Now the theorem, divergence theorem, refers to you can say a relation between the surface integral to the volume integral. When up to this point we are already discussed about the gradient, we already discussed about the divergence. Okay, two parts we have. And in divergence we have come across about this volume integral and that surface integral, if you remember. Okay, so if you see over here that it is a dot ds, the total you can say the flux uh, around the closed surface, and that can be the del dot A dV. This del dot A, you can understand that it is basically the divergence part, and this is the volume integral. So this equation basically relates a surface integral to a volume integral. So how it defines that the total outward flux of a vector field A at closed surface S is the same as volume integral of divergence of A. So this must be the B. This must be S. Okay. So A dot ds closed surface. This should be S. So this will be del dot A and dV. Right. So this is correct. This will be. So we can understand that the divergence, or we can say the volume integral of the divergence of any vector field, is equal to the total outward flux of that vector field. Suppose one vector field is there, d is equal to rho cube a rho, exists in the region between two concentric cylindrical surface, and the limits are given: rho is equal to 1, rho is equal to 2, with both cylinders extending between z0 to 5. Now verify this divergence theorem by evaluating d dot ds and d dot dv. So we can easily find that the for concentric cylinder, the left side, d dot ds, d inner, d outer, d bottom and top. So we can find where d inner is with these values: phi is equal to 0 to 2 pi, z is equal to 5, 0 to 5. So we can find a minus 10 pi. And d outer 160 pi, d bottom as 0 and d top as 0. The limits are accordingly given in the question. So if we put all these values, so integral d dot ds over the closed surface with the sum of all values what we had, 150 pi. Second solution, second example is, suppose for the right side of divergence theorem, evaluate the divergence of d, del dot d, and then put the value. So del dot v we are finding this 4 pi 4 rho square, and we can easily find it. Again it is 150 pi when we take the volume integral. So we can say that we can easily define that, okay, what is the divergence? If we take that divergence over the complete volume, that will be equal to the outward flux through the closed surface whatsoever we are into consideration. So that is the divergence theorem. That theorem is also known as Gauss divergence theorem, right? So the divergence theorem is also known as this one, the Gauss divergence theorem. Okay. So now we are into the curl of a vector. So this is entirely another part. That curl of a vector is an axial rotational vector whose magnitude is the maximum circulation of A per unit area tends to 0, and whose direction is the normal direction of the area when the area is oriented so as to make the circulation maximum. So you can understand there is a vector, and if it takes the rotation around any you can say any path, when this area is tending to 0, the complete area is tending to 0, so that value, if it try to rotate, so whatsoever the area enclosed is coming limiting to 0, so that the direction of the area is into the normal direction when the area is oriented, so as to make the maximum circulation. So it's a very interesting part. So curl of a vector is defined as the, you can say, A dot dl, the line integral A dot dl. A is the vector field. Ratio is with the small surface, but the condition is that that small surface is limiting to, it's tending to 0. Okay. So curl A is represented by del cross A. It's the vector product of del operator with the vector field, and it will be given as the limiting case of delta s tends to 0, and integral A dot dl, this is C, and delta s, and the direction is an is the in direction, you just see the normal direction of the area. Okay. So it's the maximum circulation possible. So if you see this this example over here is a rotational loop, is you can say rectangular loop. So A to B to this point, and then D again it's rotating. So A dot dl is integral AB BC CD plus integral dA A dot dl. So complete rotational part we have to consider. Now curl of the vector field is concerned with rotation of the vector field. The rotation can be used to measure the uniformity of the field, and the more non-uniform, the larger value of the curl, right? So Cartesian coordinates we can write in this way, because it's a cross product, and del and A both are having the values like AX, AY, AZ, del by del X, del by del Y, del by del Z, AX, AY, AZ. We can open it for the calculation. For circular cylinder also we are having these values: A rho 1 by rho, then matrix A rho, rho A phi AZ, del by del rho, del by del phi, del by del z. So these are the values we can easily, and then for spherical coordinates we can easily find this. Now spherical or del operator in Cartesian, and the vector itself will be in Cartesian, cylindrical or spherical. Accordingly, you will get the result. Now, according to this, because right now we are into gradient already discussed, divergence discussed, and we have already discussed the curl. Now we are moving into the Stokes theorem. The Stokes theorem basically is a relation. It actually relates the line integral with the surface integral, and it simply says that if any vector field is available, so you can understand that line integral of that vector field will be equal to curl of the vector field. Okay, curl of the vector field, but with the that surface, the closed surface, bounded by the closed surface. So circulation of a vector field A around a closed path L is equal to the surface integral of the curl of A over the open surface S bounded by L. So there is a limit of that field by that curve, and that curve is defined by L. So inside that whatsoever the surface, that surface need to be taken into account, and for that we find that curl. Okay, so curl of A are continuous on S. So we can easily find out that if this suppose a curve is available in this way, and the rotation is going through the boundary of the path, so the in the enclosed surface is here, the blue color, so that will be there. So surface S and ds will be into the perpendicular direction of the surface. So a small length element if we take, then we can easily find out. Okay, so if we take the example, right, evaluate a dot dl for this vector is in cylindrical coordinates. So example can easily be find out. We plot the graph and then we put the values, right? So we can easily find out all these values after calculating the integrals. And just moving apart, I'll directly go to I'll discuss these examples, because the integrations you have to solve. I request you to solve these integrals at your own and try to find out the results, because these integrations are simple. This Laplacian of a scalar I will discuss in my next class, and I am just stopping over here for this, because already a few topics we have covered. I am just revising. One, first we have discussed the gradient of scalar, then we have discussed divergence, then we discussed you can say divergence theorem, then curl, then Stokes theorem, and a few examples already we have seen. So we will be applying more and more when we see some practical applications of this. Okay, so thank you for this, and we will meet soon for the next class. Thank you.